So the following problem that we're going to do next states that what is the wavelength of light emitted when the electron in a hydrogen atom undergoes a transition from energy level n is equal to 4 to n is equal to 2. Okay, so first thing that we want to do is underline or highlight the important components of this problem. First off, it's asking what is the wavelength of light emitted when the electron in a hydrogen atom undergoes a transition from the energy level n is equal to 4 to n is equal to 2. So what is this asking? Well, they are telling us we have an electron that is in the n is equal to 4 state, and it is relaxing down to n is equal to 2. Well, remember from lecture, when you have these types of transitions, when you relax back down, you have to emit light in the form of energy, and this is going to be known as your photon. So we're looking at the wavelength that is currently being emitted from this transition. So what kind of formulas are we going to need to actually answer this type of problem? Well, we're going to need a handful of equations. Well, we learned the equation that uses the Rydberg constant, which is energy is equal to minus times the Rydberg's constant multiplied by 1 over n final, and this is the energy state that you end in, squared, minus 1 over n initial squared. Okay, so a few things that we want to take note of. When we go to calculate this initial energy, we are going to first calculate for the energy that is lost, that the energy that is lost from this electron from this transition. Remember that the total energy in the universe is constant. Okay, and this cycles back to the conservation of energy, the law of conservation of energy, that energy is not created nor destroyed. So any energy that we lose from this transition is going to be equal to the energy that is being emitted, so the wavelength that we're primarily looking for, is going to be emitted in that fashion. So the energy of my electron plus the energy of my photon has to be equal to 0. And this is going to make a lot of sense for when we attempt this problem. We're going to get a negative energy, and that's going to be the energy associated to my electron. Well, if we know that these two energies, when you add them together, have to be equal to 0, we know the energy of my photon is just the opposite sign, or multiplied by negative 1, in order to get the energy that corresponds to it. So let's go ahead and answer the first part of this question. We're going to look for the energy of this electron. So the energy of this electron is going to be equal to negative my Rydberg constant, which is 2.18 times 10 to the minus 18th joules. And this is multiplied by 1 over my final transition state, which is going to be 2 is my final transition state, so 2 squared, minus 1 over my initial starting point, so where that electron is initially starting at, which is 4 squared. Okay, when we calculate this out, we end up getting an energy that is equal to negative 4.09 times 10 to the minus 19th joules. Let me go ahead and erase some of this stuff on here just to make it a little bit clearer. Okay, so perfect. Right now we have the energy of my electron. It is negative. Okay, when you calculate your wavelengths and everything, your wavelengths are never negative. So this is the energy of my electron. In order to find the energy of my photon, it's going to be the opposite sign. So my energy of my photon is going to be equal to 4.09 times 10 to the minus 19th joules. Okay, perfect. We have my energy of my photon. Well, let's go back to the question and let's identify what this question is asking us for to make sure we're going the right path. Well, they ask us, what is the wavelength of light emitted when the electron undergoes the following transition? So we're looking for wavelength. Well, we know that energy is also equal to Planck's constant times frequency. Right there, frequency. Frequency is going to be the key factor in solving this problem because we know frequency is related to wavelength by the following equation. Speed of light times wavelength is times frequency. So speed of light is equal to wavelength times frequency. Well, once we have that relationship, we can start combining things. I'm going to go ahead and clear off some of this board so we can continue answering this problem. All right, so I'm going to do something, and I'm going to combine these two equations in one so we can just tackle the problem all in one go. So I'm going to solve, in this case, for frequency. And I'm going to rearrange this equation to say frequency is equal to the speed of light divided by wavelength. Well, once I have that, I can then plug that into the following equation. Energy is equal to Planck's constant times the speed of light divided by frequency. Once I have this, I can then rearrange the following problem to solve for frequency. So to solve for wavelength, I multiply each side by wavelength, multiply by wavelength, and then divide by energy. I now have the formula. That says wavelength is equal to Planck's constant times the speed of light constant divided by energy. Well, once we have this, at this point, we just plug everything in. We know these three variables. So we know these Planck's constant, which is 6.63 times 10 to the minus 34 joules second. We multiply by the speed of light constant. Meters per second divided by hopefully you guys can see that. Sorry about that. Divided by our energy, which we calculated to be 4.09 times 10 to the minus 19th joules. Well, we go ahead and cancel out the units, joules and joules, seconds and seconds, and we end up calculating our wavelength to be 486 times 10 to the minus 7th meters, which this can be written as 4.86 times 10 to the negative 7th. We can move the decimal places over 2 times to the right, and you get 486 nanometers. And so that's how you kind of attack these problems. You want to make sure that when you see these problems, you're understanding your starting point and what you're looking for. In this case, the key things that they were asking us to look for were the wavelength of the following emission from this transition. Well, we know when we are dealing with transitions, we are looking at the photon that is being released from the relaxation of this transition, of this electron transition. In this case, from n is equal to 4 to n is equal to 2. Once we calculate that energy, we can then relate energy to that of Planck's constant and frequency. And we know frequency is related to wavelength based off the speed of light equation. you can combine the two equations, or if you also had wanted to, you can do them separately. You could have solved for frequency in this case, and then plugged in, and then solved for it individually for wavelength in this scenario, using that equation. So hopefully you're able to follow along with the following steps in order to answer this equation. Oh, sorry, in order to answer this question.